Hello everyone, my name is Yoman, and I will today introduce one of the promising imaging modality, fNIRS, to you people. Well, this lecture will include, first of all, I will tell you something about the brain imaging techniques, then near-infrared spectroscopy, then what is functional near-infrared spectroscopy, the principle of fNIRS, some of the ways in which we can use fNIRS, and the advantages and disadvantages of fNIRS, then some history or background literature review of the fNIRS, and then how do we analyze the fNIRS signal. Well, these are some of the brain imaging techniques. Like we have some invasive brain imaging technologies and some non-invasive ones, some of the nuclear ones. Well, to be honest, invasive brain imaging technologies are better in terms of signal acquisition, but there are certain medical risks involved with the invasive brain imaging technologies, so most of the research is shifting towards the non-invasive ones. If we can do the same thing using the non-invasive technologies, that would be much better. So, of course, these are nuclear imaging technologies, so these are preferred. Out of these three, fMRI is usually very bulky, and EEG and fNIRS are portable and low cost as well. So, potentially for brain-computer interface, we are left with two imaging modalities, that are EEG and fNIRS. Out of these two, EEG is usually, the EEG signal is very noisy. EEG actually detects the electrical signal because of the activation of neurons, postsynaptic signals. And the fNIRS basically can detect the hemodynamic response or the changes in the blood flow because of neuroactivation. So what actually is near-infrared spectroscopy? Well, the American Society of Testing and Materials defines the NIR region as the region from wavelengths ranging from 780 nanometers to 2526 nanometers. But of course, we don't use this all region in the near-infrared spectroscopy, some part of it. And why do we use that? I will tell you later. And yeah, there it is. Usually we use 650 to 1000 nanometers, and this is the visible light region in the electromagnetic spectrum. As we go left in that, we have an increasing energy, an increasing frequency, and a decreasing wavelength. And towards here, we have decreasing energy and frequency and an increasing wavelength. So as you know that the radio waves are quite large waves in wavelength. Radio waves can be compared to that of a scale of buildings. And if we go down to the visible region or near-infrared region, the near-infrared region waves have a wavelength of around, you can say, a needle or hair, like that, in that scale. And those gamma rays are very small, they're in atomic level. So a normal human eye can respond to this region in the electromagnetic spectrum. Well, now, what is a functional near-infrared spectroscopy? Using near-infrared waves for spectroscopy means it's near-infrared spectroscopy, but the functional part is that we have two kinds of imaging techniques. One is called the structural imaging, and the other one is functional imaging. The difference between the two is that the structural imaging deals with the structure of the brain or any other body part, and the diagnosis of gross intercranial diseases. Well, intercranial means within the brain. For example, tumor and injury. But the functional imaging deals with detecting or measuring the changes in the metabolism or changes in the blood flow or chemical composition in the blood, etc., due to the response of some event or some activity. So this is the typical image of structural imaging. These are normal. This is a normal image, and we can see that there is something wrong. We can detect tumors, etc. But using this kind of functional imaging, we might not be able to detect tumors or injuries, but we can see that which part of the brain is functioning right now or responding to some activity. Well, the theory of near-infrared light spectroscopy operation goes something like this. We use, as I told you before, between 600 to 1,000 nanometer wavelength light. And why do we do that? Because in this region, in the electromagnetic spectrum, the absorption, because of the light absorption because of different chromophores present in the blood is something like this. There is oxyhemoglobin, deoxyhemoglobin, bulk lipids, and water. The water absorption during this range is quite low. We want to do so because water does not give us any useful information, and 83% of our body consists of water. So, in fact, 83% of the blood consists of water, not the body. So, what we want is to use this region in which the absorption of lipids and water is less to detect the change in the concentration of oxyhemoglobin and deoxyhemoglobin. So from that we can get to know that how much activity is there in the brain. Of course, when you will do some activity, the neurons get fired. Well, after the firing of neurons, what happens is that the neurons require glucose or oxygen to become active, and that oxygen is provided by the oxyhemoglobin. So after the firing, after there is activity, the blood flow to the blood oxygenation level flow to that area increases, and because of that increase, there is a rise in the oxyhemoglobin and a decrease in the deoxyhemoglobin, and the total hemoglobin, which consists of the addition of these two, almost remains the constant. Not really the constant, but usually it almost remains the constant.
Not the,
Yeah.
the bulk lipid means the protein?
Yeah, lipid means the cholesterol.
Cholesterol?
Yeah, cholesterol, you know?
Cholesterol.
Cholesterol, yeah.
Uh-huh.
So there are some, in fact, in a human body, there are some cholesterol, but in the brain, the level of this cholesterol is quite low. There are very less cholesterol in the brain. So potentially we can ignore this thing in context of brain imaging.
Are there some difference between the absorption of the large vessel or small vessel in this case?
Sorry, I did not get your question.
If someone has large vessel in he or her brain,
Okay.
and the small vessel in
Yes.
your brain.
Yes. There is a little absorption because of the small vessels, but that's also negligible. That's very small, because the near-infrared light can penetrate through the tissues and the vessels. But if there are large arteries, like if we are imaging our hand or legs, then that plays an important role. In case of brain, we don't have major arteries in the cortical areas. We just have small vessels. So they don't contribute much to the absorption. Andrew?
No, yeah, I have a question. Some people are expecting to measure another important signal by adding one wavelength more between the some near-infrared lens, and what they are expecting is measuring the signal of waters.
Okay.
So what do you think about that? Because you
Yeah.
told us the H2O signal is not meaningful, not usually.
Yes, that's right. So to measure HBO and HBr, or we call it O2 HB or HHB, the oxygenated and deoxygenated hemoglobin, we need to have at least two wavelengths. because using the Beer-Lambert law, the modified Beer, I'll explain later, we need to have two wavelengths to detect these, because we will have a system of two equations and two unknowns. Now, your question is that some people really want to use the third wavelength to measure the water. Now, that's a good thing to do, because in that case, using three wavelengths, we will have three unknowns and three equations, and we can actually measure the absorption due to water. And that absorption we can subtract from the original values of other to remove the error, to remove the noise. Because water is like a noise in our case. It does not give us a useful information about the activity of the neuronal firing. Neuronal firing can increase the oxygenated hemoglobin and decrease HHP, but it does not play any role in increasing or decreasing the water level. So once we get to know the water level, we can subtract it from the signal to remove the noise.
Okay. So, Norman, can you go to slide? Then this atlas will detect the hemodynamic change using two wavelengths. And
That's
the
right.
darker color means more active.
That's right.
The question is how people determine the color using.
Well, actually, that is because what we do is we find out the activity due to hemoglobin, and we find out the T values of the activity against the non-active parts, and we plot the T values usually. So later in the statistical analysis, I will tell in detail that how do we plot some T values.
If we say T values, mean we should compare with something.
Yeah, that's the rest state.
So
we compare the activity state with the rest state.
With the rest of
We can use the t-value to estimate activities of the brain, but we can use the methods to estimate activity in real time.
That's right. In case of real time, we can use the matrix and apply some algorithm. Yes. Any other questions? So here we were. Yes, so, well, apart from these, there are some other things, some other chromophores also present in the brain. Like I have mentioned here, myoglobin, cytochrome, methglobin, etc. But the concentration of these are, in fact, the absorption coefficient of these other chromophores is approximately zero or negligible during this wavelength. Right. Maybe if we use some other wavelengths, then the absorption coefficient is high. But we don't want to do that because we want to neglect the effects of those. And also, if we go beyond 900, you can see that the absorption because of water is quite high for the 900. So that's why we don't usually go beyond 900. We usually use from 650 to 900, not even 1,000. Well, this animation will tell you that how do the photons travel through the tissues. If we incident a photon in this area, it scatters. It totally scatters. Well, unlike the X-rays, which travel usually straight, not exactly straight, but the X-rays also have some scattering, but that scattering is quite low compared to the near-infrared light scattering in the tissues. So it scatters and moves moves away. So this diffusion isn't usually spherical form. So the penetration can be deep into the tissues. If we use like 10 megawatt LED or laser, we can penetrate up to 3 centimeter in the human brain, and even more in the. We can go even more deeper in the child's brain because that's a small. The head of the neanderthals is very small. So I will tell you in the next slide that how do we actually detect that light after throwing it into the brain. Well, there it is. So if we incident the light on this part in here, it will scatter in every way. You can see that there it is. It will go there and everywhere. But we place a detector approximately, if we want to image the cortical areas of the brain, we usually set the source to detector distance to be around 3 centimeters, because that is considered to be an optimal or approximately good distance to detect the cortical activities. Well, most of the photons that are detected, most of the detected photons roughly follow this banana shape, and other photons get absorbed or attenuated, so they are not caught. But the thing is that the photons do not come straight like this. They scatter in between. They go through multiple scattering and go here. So when we will use the modified Beer-Lambert law, we will have to use the distance that the photon travels to reach the detector. How would we estimate this distance? That I will tell you later. So the depth increases with the source to detector distance, and it depends on the optical properties of the tissue. In this case, we have the brain tissue. And this is the most likely volume that is described by the photons that reach the detector. That's not like the 80% of the total photons. 80% of the detected photons reach the detector.
Yeah. To emit like any of the light, you need some electronic power, like voltage or current, something like that. If we increase the power, then can we make some stronger light, stronger some photons, so that it can penetrate more depth or more sensitive?
Yes, of course we can do that. But the problem is that if we have a very high power, they can actually damage our tissues.
Even if it is just near infrared light?
Yes, of course it can.
Oh,
You know,
really?
these infrared pointers or something like that. The remote control. Your parents usually tell you not to see into the
Yeah, we all like
that, because that's not laser. That's near infrared light, infrared light. So yes, because if the intensity is too high, they can actually damage our tissues. So we usually don't do that.
So most of some commercial machines is the maximum powers.
Optimal power, I can say.
Optimal.
Yeah, optimal, not the maximum. They even don't want to go to the maximum. They leave some margin. Usually, maximum up to 15 milliwatts. Not
Maximum.
Yeah.
Nobody has yet, right?
There
Because
would
of
have
the
been some
damage.
tests, yeah, but of course, of course, people don't feel comfortable. You know, when the X-rays came, well, there was a famous person who, what he did was that he bought an X-ray machine in the early 90s, and he used to, because before that nobody had seen his bones, so he put an advertisement that you can come and see your own bones, and people were really fascinated that we can see our own bones through X-rays, but they did not realize the dangers of that. And after a few years, the first case came out to be really disastrous. He developed a cancer and his hands were amputated, some person, so because of high exposure to X-rays. So usually the effects of these kind of waves do not appear instantaneously. They appear after some time. Similarly, you know the laser treatment of the eyes? You know about it? Some people do the laser treatment of eye and they say, now my eyesight is 6/6. So, and most of the doctors who do laser treatment, they wear glasses. They don't do laser treatment of themselves because they say we will see the effect after 15 to 20 years.
Yeah.
So can you do experiment to figure out therefore the powers about the threshold of the harmfulness?
Yes, there must be some
on
experiments,
skins
but
or
there must be some experiments already done, but I'm not sure about it. I did not study that thing. But there must have been some research on that.
just this.
That's good. Now I will tell you that once we have penetrated the light inside the human brain, and it has been detected. Now what does it detect? Well, it detects the hemodynamic response, as I told earlier. The hemo literally means blood. And dynamics, you all know, the movement and dynamics. So the blood dynamic response, it means the changes in the blood flow, the changes in the concentration of the things that are present in the blood, it detects that. And we are mostly interested in these two things. One of them is the oxygenated hemoglobin, and the other one is the deoxygenated hemoglobin, because these are directly related to the neuronal activity. So we don't want to measure the blood lipids, we don't want to measure the water. These two, because these are related to the neuronal activity. So you can see that here, this is a structure of a typical neuron. There it is 1, 2. This point, this distance is called the synapse. After the action potential is when the neuron fires. After the firing of the neuron, there is some voltage generated, the action potential. Well, after the action potential, this for the generation of even action potential, this neuron needs some energy through ATPs. Well, what are ATPs? That's totally a different topic. These blood vessels present in the brain, these basically carry the oxygenated hemoglobin. These, after firing, the oxygen is taken away from these blood, and we get these blue ones. The blue ones are the one without oxygen, that are called the deoxygenated. So that's how it happens. There comes most of the red dots, and after the activity, there are more of the blue dots. So once the activity is there, the blood flow increases, which increases the level of the oxygenated hemoglobin. But initially, there is some dip, because as it starts, the process starts, the oxygen level, the oxygenated, the HPO, these decrease firstly, and then the blood supply is increased and they increase. So there is an initial dip which we are trying to detect as well. But there has not been much research on that so far. Well, there it is, what I was talking about. This is a typical hemodynamic response function, which means if we give an impulse to the body and some of the neurons fire, what would be the graph of the oxygenated hemoglobin? What graph would it follow? So first of all, it would go a little down, not shown in here, and then as it will rise up to certain value, and then it will go down, and it will not stabilize to 0 point, it will go a little down and then stabilize afterwards. Well, all of this process takes, the complete process of stabilization takes up to 21 seconds. 20 to 21 seconds. And the onset of this slope is around 2 seconds. So basically the hemodynamic response function could be, the hemoglobin concentration, oxygenated hemoglobin concentration starts to increase after 2 seconds of the activity. So there is a 2 seconds of time delay. And it takes around 5 to 7 seconds to reach its peak value. So that's a huge delay. In case of brain-computer interface, we need to classify this signal. For that, we need the whole signal, and that whole signal comes to us after 5 to 7 seconds of the activation. and that's a huge delay which should be reduced somehow. Not it cannot be reduced because that's inbuilt process, but somehow if we can detect the initial bit, we can do more advanced research.
I have a question.
Yes.
There are two response in France. We can say it's a slow response, first of all, high modularic response, and the second one is fast response. If we use the fNIRS to measure the tissue, and this technique can measure the fast response or not.
Well, actually, I will explain the fast and the slow responses in the next slides. But the answer is that fast response basically is happens because of the neuronal membranes after they fire. If we want to use fNIRS to detect just the hemoglobin levels in some other tissues, there is no neuronal firing there. In case of like we use this machine, the frequency domain NIRS machine, we can find the absolute values of the hemoglobins, the oxygenated and deoxygenated. In that case, we don't need the neuron to fire. So the fast optical response cannot be detected for other parts of the body, because fast optical response is also known as the neuronal optical response. That is because of the neurons in the brain. So no, that's not possible in the other parts of the body. Well, that's one really important thing that I have touched a little in previously. The emitter to detector distance is very important in fNIRS measurement. Imaging depth usually increases with the increase in imaging in the emitter to detector distance. And to access the cortical areas, usually the emitter detector distance should be at least 25 millimeters or 2.5 centimeters. If the source to detector distance is less than 25 millimeters or 2.5 centimeters, it might not go deep enough to measure the changes in the cortical areas. It might just come back from the upper part of the brain. So you have to, usually, you have to maintain a source to detector distance of more than 25 millimeter, and as I told you before, we usually take it as 30 millimeter or 3 centimeters. So and also it should not be more than quite more than 45 millimeters, because in case you have put very far the two electrodes, what happens is that the signal that arrives at the detector, it might become too weak to be usable, or it might not arrive at all. So you never know. So you have to choose an optimal distance, and usually for the cortical areas, like for prefrontal or the motor cortex, we use 30 centimeter usually. Well, here it is, the thing that you asked about, the slow and the fast optical response. So fNIRS can actually potentially measure two kinds of responses in the human brain. One is called the slow signal, which I have explained you now before. We were talking about the slow signal so far. We have not touched the fast signal yet. And the other one is the fast signal, also called the event-related optical signal, EROS. Well, as you saw already, that the slow signal, it takes two seconds to respond, and then it takes around 5 seconds to go to its peak value, so it's quite slow. But the fast optical signal, it goes in the milliseconds. Well, how is it produced? Well, what happens is that we do not, in the case of fast signal, we do not measure the changes in oxygenation of the hemoglobin, but we measure the changes in the light scattering because of neuronal firing. When the neuron fires, there is some changes in the membrane of the neuronal ensembles. Because of that, the membrane of the neuron and the surroundings, their optical properties change, and we try to detect those optical properties and get some signal out of it. That is called the fast optical response, event-related optical response signal, or sometimes the neuronal optical response. So as it is written here, it detects the changes in the light scattering, changes in the size of the membrane or the membrane optical properties,